Yeah, my talk is fairly brief, and I'm not going to say too much that people haven't already said at this meeting. So you can safely take a coffee break for the next 15 minutes. Um, this slide just goes over some of the sample return missions over the past 60 odd years, and we're obviously living in a time when we're having them much more frequently, which is really great. But this talk is about next slide, please. And this slide, although the title is why we actually need to do sample returns when we have so many meteorites. Uh, this is actually kind of a cautionary, scary talk about some of the scary things you learned about these astromaterials recently from these return samples. Next slide. So, of course, we all know that these return samples are really great, not just because we can analyze them immediately and learn new things about the samples, but also because we can do things with the samples on the ground you can't possibly do remotely. And as long as we take care of these samples, do good curation, then it means that our children's children can take advantage of these samples in the future when they can do much better things and test new analyses and new hypotheses, as long as we take care of the samples. And of course, you can say the same thing about meteorites, which we now have many of, at least 70,000. Last time I checked, there's probably a lot more now. So how are these return samples, in fact, more useful in some cases than the meteorites? And again, the obvious answer is because these return samples, if they're carefully collected and returned to Earth and curated, have seen much less terrestrial alteration. And next slide, please. So we know already that samples on Earth are really ravaged, and I use that word purposely, by terrestrial alteration, especially oxidation and hydrolysis. Anyone who deals with analyzing meteorites knows that, especially for really old falls, you have to be very careful about rust and things like that. Anytime you measure things like porosity, permeability, you have to take that into account. Often that isn't. And although you can minimize these problems and try to understand them, you can't do that good a job with them without looking at samples that have not been analyzed or not been affected at all by terrestrial alteration. Next slide, please. So we had some suspicion this was the case, not just from rust, but also other features. When I started looking at meteorites, 40 plus years ago, looking at aqueous alteration, people were wondering about the extent of aqueous alteration and how pervasive the fluids had been moving through these samples. And the poster child for that was the CI chondrites, which had these, centimeter long and longer veins of sulfates and carbonates, mostly sulfates. And that was taken as a measure of the extent of the fluid movement through these samples, with very little thought for whether these sulfates were in fact had to be pre-terrestrial. And some indication that there were some problems. I remember Ed Anders was telling me that he thought about this problem back in the 1960s, and he had a problem with looking at the aqueous alteration extent, looking at the chemistry of that and the oxidation state, and to go from most of the minerals you see, the secondary minerals like the phyllosilicates, secondary sulfides, carbonates, but then to step to the sulfates required orders of magnitude higher FO2. And he was at a loss to figure out how that could have happened. He was trying to figure out maybe some organic reactions that occurred to cause that to happen. So that was kind of a problem, how you get these changes in FO2 to make these sulfates. And then Don Brownlee loaned me a sample of orge many years ago, and I took it out after about 10 years, looked at it. It was covered with sulfates. And I thought, well, that's kind of strange. So next slide. So Matt Gunnell did some careful detective work. This is back in the 1980s and early 90s. Went back to the early records of the fall of orge, for example, and found that, in fact, the earliest investigators reported that the samples were entirely black, like coal. And there's no indication of any things that were white clusters of things on the sample. So no sulfates whatsoever. And these were very careful chemists looking at these samples. They wouldn't have missed something like these. So we proposed that, in fact, these sulfates were entirely terrestrial in origin. Maybe they weren't all terrestrial in origin, but we made that claim. And about the same time, I also proposed that maybe these iron oxyhydroxides you also see in not just CI chondrites, but really in all C chondrites, and particularly the ferrihydrite. Maybe this is also entirely terrestrial in nature. And that was based on some observations of scientists who are looking at saponites pulled from the bottom of the Red Sea. And they x-rayed these samples immediately and found that the saponites were entirely Fe2 plus containing saponites. But within a few minutes, the saponites changed color. They x-rayed them again and found that all the Fe2 plus was now Fe3 plus. And there was now a lot of ferrihydrite in the sample, which appeared because once you go to Fe3 plus, you can expel the iron from the saponite to preserve charge balance. This happened in a few minutes. And so this is entirely unavoidable for samples that are falling. And I also found that would also explain the compositions of the saponites and the ferrihydrite in CI chondrites. But no one liked that explanation, so it's kind of forgotten for a long time. But I still think that the ferrihydrite is terrestrial alteration. Next slide, please. So the question now becomes, how much of these oxyhydroxides and sulfates are of terrestrial origin? Are they all of terrestrial origin? And so as we had falls of C chondrites over the years, I've always been looking to see if, as we get fresh samples, do we see sulfates or ferrihydrite in them? And my experience was that they really didn't see these in Tagish Lake, Sutter's Mill, Aguas Arcas, Tarda, or other freshly fallen C chondrites as soon as they fell. And I propose that people should look at these samples periodically over the years to see if they're appearing. And I'm not sure that's being done, but I suspect they are. I know that chondritic IDPs I mounted in epoxy years ago, back in the 80s, and microtomed, and then stored in nitrogen. They now mostly have sulfates sitting on top of them. So when I cut those samples, there's no sulfates in those at all. Those have all grown over the years, even in samples stored in nitrogen. Next slide, please. So all these samples have been in the Earth's atmosphere. And so even in samples that are recovered immediately on the ground are beginning to alter. So it's only in the return samples that are very carefully maintained during return to the atmosphere and curated where you have a chance to check whether these phases are really pre-terrestrial at all. And I know some scary things. So during Hayabusa sample preliminary examination, I was actually in Japan during the pandemic for a month, and we're in the SCM looking at some samples, and one sample had tiny sulfate crystals growing on the surface. So they were sitting on the surface of the sample. Next slide, please. And here's some pictures of those. The scale bars, which you can kind of barely see, they're all 10 microns. And it happened that this particular sample had fortuitously been analyzed by X-ray CT as soon as they recovered the samples from the container. And in those images, they could not see any of these sulfate crystals in the sample, and they would have. And so these are clearly growing on the sample, even though the sample was kept at nearly vacuum conditions on return to the atmosphere, not quite, close, and was stored in a vacuum for the most part, or nitrogen. And still you're seeing sulfates growing on the samples, and I suspect also ferrihydrite forming as well. And so despite the best efforts to keep these samples away from the atmosphere, even tiny amounts of atmosphere were getting in and causing these changes. This is a pretty scary thing. And what this means is that future missions really have to do as good a job as they possibly can to hermetically seal the samples after collection and all the way up to curation in the lab. Because the best efforts of humans are never perfect, but they can be improved through time. So it's kind of a warning for all future missions that they really have to do this if they want to worry about analyzing things like porosity of samples, FO2 conditions of secondary alteration, those things. If you worry about those, you have to take these phases into account and worry about what could be happening to the samples on the ground. Next slide, please.
5 minutes.
Okay. So I could already said all this. Next slide. And another scary thing is that these samples are extraordinarily reactive. I'll just go on next slide. So Noguchi-san noted that some samples from this is from Itokawa samples. So this is that he had, well, I guess he microtomed these samples. They're sitting on copper grids. He looked at them in the TEM, then put them away and stored them in a vacuum for, I think, 6 months, and pulled them out again, looked at them again, and saw the copper sulfur oxide bearing phases, undoubtedly copper sulfates, had grown on the samples during the time they were stored in a vacuum. So these samples were interacting with apparently with the copper grid that they're sitting on in a vacuum chamber in a stainless steel container. So that just shows you, and also he sees tin oxide in the samples as well. And so these samples are incredible because they're sitting in a vacuum for so long and weathered by radiation, et cetera, right? They're incredibly reactive. And so your best effort to keep them clean is going to be not going to work entirely well. So that's a good reason then to start preliminary examination of these return samples, the instant they return to the ground, and not to wait for weeks or months before you begin to do these analyses, because they're going to be changing even despite your best efforts to prevent that. Next slide, please. Yeah, I said this already. Next slide, please. And people have already mentioned space weathering. So I'll just say that space weathering is here, and that's the reason you're seeing these very, very reactive samples. Next slide. And aqueous fluid inclusions, we've fairly easily found them in sulfides in the Ryugu samples, and they undoubtedly were present in probably most sea chondrites that have fallen, that have seen water on the asteroid. And yet they're very, very elusive in meteorites. We've only seen them in a few samples, and usually very, very tiny. And this could be due to terrestrial alteration as well. And so it could be that our search for fluid inclusions and other secondary phases is going to be better performed with these return samples than with any meteorites, unless even ones that are recovered immediately on the ground and brought to the lab and analyzed very, very fast. Next slide, please. So conclusions, space weathering is a significant factor in these samples. It's very, very rarely exhibited in meteorites, but it's common in all these different samples. So that's the place to study them. And these samples are phenomenally reactive with the Earth's atmosphere. And so return samples, they're superior to meteorites in many respects, especially respect to effects of oxygen and water, and must be collected and maintained as close as possible to conditions on their home worlds. That means bringing them back in a vacuum, or at least hermetically sealed as well as we can. And of course, as you've seen before in Tomoki's talk, difficulties remain, and also other talks of this session. Difficulties remain in interpreting reflectance spectra of asteroids due to all these effects. And another reason that these samples are so important to look at is because they give us a Rosetta Stone for figuring out, how these asteroids are different from the meteorites, and helping us to then leverage all our reflectance spectra and understand the asteroids much better. But there's still a lot of work to be done there, because it looks like all these asteroid types, space weathering processes are different in each case, which is a big problem. So another reason for returning more samples from different kinds of asteroids, not just always S and C type asteroids. And the majority of asteroids are still poorly understood. They've only sampled 3 so far. We've got ways to go to get up to 1 million. And I'll just stop there. Thank you.
Okay, we have time for one quick question. If anybody has a question they'd like to ask Mike.
Hey, Mike, it's Paul Abel.
Hey,
Quick question for you. Given all this, what do you think are the best techniques for, I mean, apart from studying the samples quickly upon the return, what's the best way to store these to prevent them from
yeah,
altering?
there's no best single way. I mean, I have samples stored in nitrogen, others use vacuum, and all these see changes occurring in the samples. So the best way is to store them in several different containers. Vacuum is one. Another would be nitrogen, where you carefully analyze nitrogen. You're actually working with the sample with, and then comparing those. There's no single best way to store them, unfortunately. Uh, I guess
What
the
about
best way is to store them in space, right? Analyze them in orbit, right? I mean, it'd be ridiculous there, but I think there's no human built container, simple containers or storage techniques. They're going to be perfect.
what about cold? Keeping it cold
Yeah, cold.
temperatures.
That's a good question. It's kind of a scary thing to do that, uh, to store them cold. I mean, you could also be changing mineralogy. I could go back to for Tagish Lake. We stored some samples using dry ice. That causes samples to crack apart and break. And so, even storing them cold, you have to give some careful thought to how you're going to do that. How about samples from Venus? Would you store them hot?
Yeah, I don't know. Anyway, thanks. Appreciate it.
That's a great question. Cold's a good idea, but it's not a slam dunk. Just freeze it and you're safe.